take it like in the fall, spring.
Yeah, take it
It's just
towards
sports.
Yeah, so that's what it is every week.
Yeah, now he gave us, he had to buy this book with questions in here,
Yeah.
and the test is 5 questions from the modules that we went over.
Yeah, that's the book that we use for sports.
Yes. So like, it's 5 questions from all of them, and then the questions, and the modules like exactly those questions,
Yeah.
so.
We'll do the problem just so everybody will see if we had questions about it, be taken care of. Today we're gonna do arrays, we're gonna do a couple things, polarization efficiency, and the receive power. There's 3 topics I want to take care of today. But first, about this problem. I had a problem where I had one antenna sort of like this, I'm gonna exaggerate, and it was a half wavelength, lambda over 2. And I said that this antenna was radiating, you can tell me if this is right, a certain power, I think it was 80 watts, is that right?
Yep.
And then I had a distance here where R was equal to 1,000 meters. And I had another antenna, and I actually forgot the length of this, lambda over 10, was it?
20.
Lambda over 20. And then I had a couple of angles with respect to the normal. This one was angled at 70 degrees, and this one was angled at 60 degrees, right?
Yes, sir.
60 degrees to the normal. Now, what you have to understand, the maximum amount of power transmitted would be when that angle's 0. Follow me on this, class? And I think I had it like, isn't it like this, or is it?
It's like that.
Is it 70 degrees from the vertical or from this? Is this 70 or is this 70?
The bottom one, so.
Yeah.
From, measured from this point to there, right?
Yeah, so that first antenna is like this.
It's tilted heavily.
I think it's
But
actually tilted
the other
way.
direction.
And then
It's tilted the other direction. And they're both tilted away from each other. Yeah. And the other one's
And now is
now the
this
bottom.
angle 70?
bottom angle.
Bottom
70.
angle.
Bottom
70.
angle 70, that makes sense.
Yeah, and then the other one's tilted the
And
opposite
then,
direction than right now.
And then, this, let's see, this angle was,
60.
no, it has to be up here. It has to be less than 90, right?
Well, no, because that antenna
That one is
tilted
this way, but
so the bottom angle was 60.
So this one's
Yeah.
60. Okay,
yeah,
now we're going. And that was lambda over 20.
right.
And the whole idea is find out what the received power is here, right?
Yes, sir.
Alright, well, this is just used, it's an application of freeze. So first, recognize that's a half wave antenna, therefore the actual gain of this antenna is equal to 1.64 times, and then it's the cosine of pi over 2 cosine of this angle, and I'll call it theta, but it's the angle with respect to the perpendicular from the antenna, over the sine of theta, and that's all squared. This one is a short dipole, so the gain of this, really this is directivity. I'm assuming it's gain because I didn't say,
Is it not over sine squared theta?
yeah, the whole thing's squared.
Oh, okay.
Alright, I wanna say this too. I'm assuming the efficiency is 100% of 1. If I don't say the efficiency is less, you have to assume it's 1. Follow me, class? So then, the gain here, on this one, the short dipole, this is the transmitter, the gain of the receiver was equal to 1.5 times the sine squared of theta. And after that, we just go right to the calculation, P received is equal to P transmitted, right? And I can do it this way, P transmitted over 4 pi R squared. Now that's simply the isotropic radiated power density. And then I multiply it by the gain of the transmitter, I'll call it gain of the transmitter there is going to be 1.64 right? And then it's gonna be times cosine of pi over 2 cosine of, and it is that angle, right, of 70 degrees, over the sine of 70 degrees, all squared. Now that's the amount of power density that's actually incident right here. Now, I'm not using Friese just the way they have it, I'm doing it step by step. So if I asked you on a test what the power density is right there at this point, this is how you get it. Then I'm gonna multiply it by the effective aperture. Now this thing is not, it's not oriented for maximum received power. It's off base, so you have to use the reduced gain. And that would be times that gain right here, times 1 point. But what it amounts to is it's gonna be the gain squared. Let me get this one. The aperture, the effective aperture is equal to lambda squared over 4 pi times the gain. The gain I'm using is the reduced gain because it's not normally incident. It's not coming in for max gain. Does everybody understand what I'm saying in class? With me? So, with me on this? All right, so this is going to be equal to lambda squared, and the frequency is 1 megahertz, right?
Yes, sir.
And so lambda is equal to C over F, and that's gonna be 3 times 10 to the 8th over F is gonna be 10 to the 6th, so that's going to be equal to, that's 300 meters, right? So it's lambda squared, or 300 squared over 4 pi, and then it's times the gain, which is 1.5 times the sine squared of that angle, which is 60 degrees. Now, if you do this on your calculators, I think you get about 0.7 something, is that right? Can you just go ahead and run the, are you with me on this, what I've done? Everybody? I mean, yes, sir.
Why is the gain on the receiver just sine squared theta and
It's
not
a-
that cosine pi?
Well, remember, that's a lambda over 20, that's a short dipole, right? It's not a halfway dipole. Short dipole, the gain was 1.5 times sine squared, wasn't it, class? Are you with me on this?
Yeah.
All right, can somebody run this calculation? I think it was 0.704 or something like that. I've got it on MathCAD if you. And you, buddy. Josh is doing it, you're doing it. Transmitted power is 80, but I don't think it was a Erad. Anything?
I mean, that's what I did, and I got like 95 milliwatts.
Check it out. Is that what you guys did?
I didn't do that.
Yeah, we-
gained at the receiver. I didn't.
Yeah,
I
we
used
accidentally did the,
Yeah.
halfway dipole.
I used the
equation for
halfway.
that gain.
Yeah, I did the same thing, I
That's-
used the,
It's a short dipole.
That's
yeah, I had
that's
the
level.
equation, I had the
What do
1.5
you,
sine.
just tell me what you get, what?
I got 95 milliwatts.
Did you run it again, the
Oh,
calculation?
I didn't run it again.
I just wanna make sure that at least with this numbers, remember R is 1,000, so R squared would be 10 to the 6, right? 4 pi, 10 to the 6 downstairs. And remember those gains involve the squaring of that angular thing, right? What's the sine of 60 is what?
Sine of 60 is just 1/2. Right?
Sine of 90 is 1, sine of 60 should be square root of 3 over 2, isn't it?
Yeah.
But just go ahead and run the calculation. I wanna make sure, at least we all agree. Remember, short dipole, much different than halfway dipole. You may not get points, you may get something different.
I'm getting 75.9 milliwatts.
milli? Is that what you guys are doing? 75?
Yeah, but 89.
Yeah.
I got 95 milliwatts again.
You got 95?
I got 98.
Just square.
Yeah,
half.
alright, I'm betting it's that.
Get it, just figure that.
Yeah, just
Okay.
like, just do it like this, where you do it.
1095.
And square.
98 to 95 milliwatts.
Yeah.
Don't
okay.
put
All right,
the square
I'm believing
after the
that.
sign, because then it doesn't recognize it as a
I
sign.
believe it, yes.
Okay.
I will say one thing, you've gotta make sure the length of the antenna is considered. Apparently, a lot of people look at it both as half wave and they're not. One's half wave, one's short, and that's very important. And, cause I'll have problems where I have a half wave and a loop antenna, or a half wave and maybe, maybe a three land over two antenna, something like that. And you have to be sure you know what the actual equation is for gain associated with that antenna. Okay, so that's the problem, and that's how it's done. All right, next thing I'm gonna do, there's a couple of things I want to cover. I had a list of, got arrays. Yeah, I'm gonna start with arrays today. Now, we did Friis transmission equation, and we looked at different typical antennas. We looked at the small loop, the short dipole, and the half-wave dipole, and in the general dipole equation for any link line, what you would get. But the three most common are short dipole, half-wave dipole, and the loop. They're very, very common antennas. They're easy to understand. All the other antennas that are like, they're aperture antennas, horns and things like this, have relatively high gains, and the equations for those are well defined. But that comes later. So now, what we're gonna look at is arrays. I'm gonna explain this a little differently than Dr. Wentworth's book does, but I think you'll appreciate it. Now, when you say an array structure, you mean that the antenna element itself is going to be the same at each position, but you can change the actual phase or magnitude of current or both. So what I'm gonna do is simply this. I'm gonna say that I have a long line, and then I have a series of isotropic antennas. Use this, just isotropic for now. The first antenna has I0 on it. The second antenna is spaced a distance d from it, has same magnitude times e to the j alpha, so there's a phase change. Then the distance down d as well here is gonna have I0 e to the j2 alpha. Come down d here, and it's gonna be I0 e to the j3 alpha, and so forth. And all the way down here, 4 alpha plus all the way down to the end. And when you get down to the end, you're gonna have I0 times e to the j, and then it would be really n minus 1 alpha. So the total length of the antenna this way, L would be equal to n times d, the distance. This is a typical thing. It's just a long array of antennas. And there are both one-dimensional, this would be a one-dimensional array, and there are two-dimensional array antennas. Did anybody ever see the movie Contact? It's a long time ago, at Jodie Foster. Well, there's a picture down there where they're at Arecibo National Labs, and there's also at it's a astrophysicist site, and they had a giant bunch of dish antennas, but it was an array of dishes. Now, the reason for that is dish antennas have huge amounts of gain, 80, 90 dB. With an array of them, you're gonna see the amount of gain you get is multiplied by n squared, the number of elements squared. So if you have 100 elements, you're gonna get 80 dB plus, think about that, 100 squared would be a total of 10 to the 4th, right? Which is 40 dB, or you're gonna have 120 dB again. You need that for deep space work. If you're going into deep space, you need 10 to the 12th type of gains for any type of deep, for astrophysics. Anyway, this is the structure. Can you all understand this? There are a bunch of different, these are just localized antennas, and we're gonna assume they're isotropic radiators for now. Are you with me, everyone? Tell you what, you get the idea, I'm just gonna put down, I'm gonna do this a little differently. I'm gonna do it this way, keep watching them. I'm gonna put a line down here, and I'm gonna make the spacing a little greater, so you can see it. This has I naught, this is I naught e to the j alpha, this is I naught e to the j2 alpha, I naught e to the j3 alpha, and so forth, and there are n elements. Can everybody at least get an idea what I'm doing here? Now they're all spaced by d. I don't think I need to keep saying that, but that's d, this is d, this is d, this is d, and so forth. Now what I'm gonna do is say I'm gonna draw a radial distance r, and I'm gonna assume something. I'm gonna assume that r is much, much, much greater than n times d. So I'm a long way from the array. All right, now the reason I do that is now when I'm out there, I'm gonna say the electric field out here is proportional to the current I, inversely proportional to r, and it also has the phase e to the minus j beta r here, and it will be in the a theta direction. You'll notice with isotropic radiation, I have no angular function there. It's the same in all directions. Is there such thing as an ideal isotropic radiator? No, not really. The closest we can come is, say, the sun, something like that appears to radiate the same in all directions, but not exactly. You follow me on this? This will give you at least a visual construct for it. And the reason I use isotropic is because it's much easier to start there and explain how the element itself, when you put, say, they're all quarter wave dipoles or half wave dipoles, how it will affect. Now that's the electric field from the first one, right? The electric field from the second one would literally be at the same point. It's a long way away. It would literally be superimposed at a great distance away. So you could kind of draw it like this, but I don't want to. I'm going to draw it like this. And I want you to notice something. The distance difference here, if this is theta, this distance difference here is really d times cosine of theta. Do you all see that? So I could say this second, if this is r, I could say my r here, call this r0, r1. r1 was equal to r0 minus d times cosine of theta. It's because these are basically parallel. And the way you always think about this is, suppose I'm looking at a star and I move 5 feet away. Well, the azimuth and elevation to that star is the same. There's no real apparent change in my direction. Do you follow me on that? That's the reason. They're parallel rays. So this would be R1 would be R naught d cosine theta. And what would R2 be out here? Just think. Now the distance difference is that, right? You all see that, class? If the distance between this one and this one is really d cosine theta, when I move to this one, then it's going to be what? 2d times cosine of theta, right? So then I can say that R2 is equal to R naught minus 2d cosine of theta, and the pattern repeats itself. R3 would be equal to R naught minus 3d cosine theta, and so forth. Do y'all see this, class?
Is it 2d or d divided by 2?
Well, if you look here, this and this would be 2d this way, right?
Okay.
Then it would be times the cosine of that would be this way. All right. Now, what I'm going to do is say the total electric field at a distance would be equal to, and I can see the value of I and R. Oh, I didn't say this, but if you're a long ways away, the difference between 1 over R is approximately equal to 1 over R minus d cosine of theta, or 1 over R minus n times d cosine theta, because this is extremely small. We're talking about being like a mile away and the antenna being of the order of a foot. You follow me on this? So 1 over a mile is about 1 over a mile minus a foot. It doesn't matter. So I can take the I naught outside, or call it I, and I can take R out in front. Now, this term e to the minus j beta r is interesting, because for the first one, it would be just e to the minus j beta r. I'm gonna leave that there, times 1. Now watch what happens to the second one. If I talk about the electric field from the second one, it would be equal to I, then there's the phase shift, e to the j alpha over r. 1 over r is about the same. And then it's gonna be times e to the minus j beta, and then it's r minus d cosine of theta. Do y'all see that? Because the phase difference, now when I have r minus d cosine theta, that will have a pronounced effect up here on the phase. So if I bust that out, I can say that this E field is actually given as I over R, and then it's E to the minus J beta R. Now watch, I'll take this J alpha inside here, and then it's gonna be times E to the J beta R, beta D cosine of phi, not theta, plus alpha. Just take a look what I've done. E to the j alpha I bring inside there, right? And when I do this, I get j beta d, try to make that a little better, times cosine of phi plus alpha, right? Y'all see that, class? Can you see it in the back there? That's the second one right there. So when I talk about my total field, I'll take the e to the minus j beta r there, and then it'll be plus e to the j, and it would be quantity beta d cosine of phi plus alpha. Any guess what the third one is going to be? I bet you see it. Well, what's the big difference? The third one would have I over r e to the minus j beta r, correct? But then it would be e to the j 2 beta d cosine alpha, cosine theta, plus alpha. You'll notice that the phase shift is progressive. That's e to the j alpha, this is e to the j 2 alpha, this is e to the j 3 alpha, and so forth. So I'm having a progressive phase shift, which is very common for beam steering, and that's what this is really about, beam steering and increasing the gain. When I'm talking about beam steering, I'm talking about electronically changing the phase on all of them in a way that's synced so that the proportional amount changed on all of them will be the same, and I can redirect the beam anywhere I want. So the next one is going to be e to the j, and then it would be 2 times quantity beta d cosine of cosine of phi plus alpha. And after that, e to the j 3 beta d cosine of theta, of phi plus alpha, and plus dot dot dot, and then it would be e to the j quantity n minus 1 beta d cosine of phi plus alpha. Y'all see that? Here's where we do something that's nice. Remember that angle phi would go somewhere between 0 and 180 degrees, right? So it's not the phi that you're used to thinking of in the XY plane. You could have negative values, but the pattern just repeats itself. It'll always be symmetric. So follow me on this. What we do here is something that try to makes this thing more manageable. We create a variable called psi, and we call this beta d cosine of phi plus alpha. What that accounts for is beta, which would be 2 pi over lambda, times d, and d is usually given in wavelengths. So 2 pi over lambda times d in wavelengths always means, what that gives us is some kind of it's going to be in terms of fractions of pi. One other thing, they don't space antennas more than a half wavelength apart, because if they do that, then what you end up getting, let me just shut this off, I apologize. No matter what I do, well, this phone, I don't know why it does it, it shuts off and restarts all the time. And when it does that, it doesn't matter if I muted it or not, it's not muted after it restarts. I don't know if you ever had a phone like this, I need a new one. I haven't got there yet. So let me just put this down here, the E total, using isotropic elements, from this would really be equal to I e to the minus j beta r over r times the summation of e to the j psi, j small n psi, where small n goes from 0 to n minus 1. Do you follow me on this, class? Because all these things right here just become psi, the beta d cosine phi plus alpha. Follow me? All right, now work with me here. Some of you who, well, you've had me, Josh, but I don't know, I guess nobody else has. And I'm gonna come over here and do this to make sure everybody gets this. All right, some of you remember this. Do you remember when you have a summation of a to the n from n equals some value, say 0 to n minus 1, how to do that? It's a geometric sum. Does anybody remember that? Josh, you probably remember. I'll show you this one time because I like the cleverness of it. There's a guy named Gauss. Josh, did I ever tell you a story about Gauss in class? Do you remember that?
I can't remember.
All right, I'm going to tell you about this. This is one of the things that drew me to engineering and drew me to science in general. I love it. I love cleverness, and I always admired clever people, and people that could circumvent work by being clever and thinking by a shortcut, you might say, but without, compromising. So little Gauss, do you know who Gauss is? Probably one of the greatest mathematicians ever, and a physics, contributed to physics and probably chemistry and other things. But when Gauss was in about a second or third grade, and I'm used to this too because I was raised Catholic, but they would, in a Catholic school they do this. When they want to grade papers or something, they'll give you an assignment that is a lot of redundancy and they know the answer to. So they ask these kids to add up all the numbers from 0 to 100. Now that takes a lot of time if you just are in second or third grade and just learn how to add 1 plus 1, 2 plus, because then you got to write them out and keep adding. And it takes about 20 minutes normally. But Gauss didn't do that. Does everybody know what he did? What Gauss did is he wrote all the numbers, 0, 1, 2, 3, ... 100. Then below it, he wrote them all backwards, 100, ... 0. And he summed each column. And each one, if you think about it, 0 plus 100 is 100. 1 plus 99 is 100. 2 plus 98 is 100. So he had 100 101s. Basically 101 hundreds. So he multiplies 100 by 101, but that's twice as many values, right? You follow me what I'm saying? So he divides by 2 and he gets the answer in less than a minute. He's a very bright boy. Goes up, shows the teacher. The teacher's shocked. How did you do that? He showed. At that point, the teacher realized he's a little beyond what I'm used to dealing with. So she took him to, I guess, ended up with some professor at that time in France, I don't know if it was Germany or France, but somewhere in Europe, and they realized he's a savant, and they basically gave him carte blanche. He could do whatever he wanted, and he did, and he revolutionized so many things. Gauss's law, we used, guess who? And many other things. You got to read the history of Gauss and some of the other mathematicians. I mean, Einstein admittedly he had the insight to think deeper about a problem of modern physics than most. When it comes to really some of the most crafty, sharp people, they're mathematicians. And Gauss was one of them. There's Hilbert, there's a lot of others. And I love reading about it. Well, this is one, I don't know who did this one, but this is one of these clever little things I could see somebody thinking of. So if I want to sum all that thing, I know really what this is equal to is a to the 0, right? Plus a to the 1 plus a to the 2 plus a to the n minus 1, right? Just adding all up. Well, if I take this summation, something, you don't have to write this down, just follow me on this, of a to the n, and then I multiply it by 1 minus a. Just follow me on this, okay? Now I know I multiply this times this, what I'm gonna get is, well, that's just a to the 0 plus a to the 1 plus a to the 2 plus dot, 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 plus a to the n minus 1. That's the first part, right? That's this times this, correct? The second part, when I take this times this, then it's going to be minus a to the 0 times a, or a to the 1, plus a to the 2, plus a to the 3, plus dot, 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 plus a to the n. Y'all follow me? Now what do you notice happening? A0, no A0, A0 stays. A to the 1, there's an a to the 1, it goes. A to the 2, a to the 2 goes. Everything gets canceled except a to the n. So now it's minus a to the n. And what does that equal? Well, that equals the sum of that series, a to the n, from n equals 0 to n minus 1, times 1 minus a. So if I divide this by 1 minus a, lo and behold, I have that. Y'all see that? This is just one of these clever tricks. Mathematicians are real good at looking at these things and coming up with ways to do this, manipulation. There's probably other ways to do the same thing, but this is the one I like. Y'all see what I've done there? So that means I can do this geometric sum fairly easy. When I look at this right here, my sum is not a, it's a summation from n equals 0 to n minus 1 of e to the j psi to the nth power. So it's e to the j psi to the nth power. Do you all see what I've done here? I've taken out the n as the superscript, as the exponent. Well, what's that going to equal to? Well, that's going to equal to a to the 0, or 1, correct? Anything to the 0 power is 1. So it's going to be 1 minus, and then it's going to be a to the n, or e to the j n psi, all over 1 minus e to the j psi. Are you with me on this one, everyone? Now, some of you who remember signals and systems remember seeing something like that. That had signals and systems. I didn't teach anybody but you signals and systems, right? Nobody else had me here. Oh, I taught you. Well, at this point, you realize that that is a very often encountered kind of function. Do you remember what I do next? You're looking at the book, you probably do. What I'm going to do is turn this something into something that's understandable. Now watch, if I factor out on the top one, e to the minus, or e to the plus j n psi over 2, then I get e to the minus j n psi over 2 minus e to the j n psi over 2. And on the bottom one, if I factor out e to the j psi over 2, I get e to the minus j psi over 2 minus e to the minus, or plus j psi over 2. Do you all see what I've done there? And you probably know why I did that, because what does this look like? Well, what is sine of theta in terms of, better yet, sine, what is the sine of theta? Isn't that equal to e to the j theta minus e to the minus j theta over 2j? Right? All right, look at that. The order is opposite. I have e to the minus j n psi over 2 minus e to the j n psi over 2. So really what I could do is this. Agree? And that means this right here is really minus 2j sine of the argument. So I can write this as simply e to the j n psi over 2 over e to the j psi over 2. And then times, and this would become minus 2j times the sine of n psi over 2. Over minus 2j, the sine of psi over 2. Now on purpose, I didn't cancel the minus 2j's, but you see they will cancel, don't you, class? Now this is simply a phase term. Has nothing to do with magnitude. The magnitude is in there, or this entire thing, just for the isotropic array, the entire thing says that the electric field will be equal to I, write this down, times e to the minus j beta r over r, that's for an isotropic element. Then it's going to be times this, which is e to the j n psi over 2, over e to the j psi over 2, which is really going to be e to the j n minus 1 psi over 2. And then it's going to be times sine of n psi over 2 divided by the sine of psi over 2. And we'll call it in a theta direction, but that's irrelevant. So that's what the electric field would be from an isotropic array of radiators. All with the current I, with a progressive phase shift of alpha. Each one is alpha, different than the other, but it's progressive, right? I gotta make some comments here. The key to this is this right here. Now, I'm gonna talk about that. I should tell you one other thing. I know if you're students, you don't have a lot of free time, at least you shouldn't have a lot of free time. There's a couple of books I recommend that you read if you're interested in like cleverness and insight. One of them is by a guy named Richard Feynman. Do you know who Richard Feynman is, anybody? Dr. Richard Feynman. He got a Nobel Prize for quantum electrodynamics. He's one of the most hilarious people. He almost should be in a different area. He's brilliant, and he was at Caltech for years. He was at Cornell before then. He also worked on the Manhattan Project. Do you know what that is? What is the Manhattan Project? The first nuclear weapon was formed. He was one of the guys there, and he actually cracked safes illegally for kicks there. He found a way to do it. I got to tell you, this guy got more mischief, more trouble than anybody on the planet at that time. And there's a book called Surely You're Joking, Mr. Feynman. You want to read that'll captivate you if you love science. That's it. The second book is by a guy named, it's Paul Erdős. And Paul Erdős, I'm thinking of how to spell that last name. He's probably he's the greatest mathematician in the last 50 years at least, maybe 100 years. And this guy is somebody that is, you know how it seems like the more intelligent you are, the odder you are at times? Look at Einstein, he never wore socks, he had hair, I mean, he had hippies hair back then. And, I mean, he was just he stood out no matter where he went. He was a disaster in a lot of ways in terms of his dress and his overall behavior, but he was a genius. And that seems, the more creative you are, the more creative genius, the odder your habits and patterns. What Erdős is like this. And he's got a book, and it's called The Man Who Knew Infinity, and it's a phenomenal read. And what it is I don't know if you do this, when I was where you were, I used to start reading these books. And when I was doing my PhD, my professor gave me a book called The Masters, and it's all about over in England and how they had this structure of honor, and the people that were the masters, the people that taught everybody, they had to go through all these extraordinary exams, and everybody got clobbered, and only the very, very brightest and best survived. And it goes through in details mathematics and physics at that time, and how, I mean, they looked down at people. You wouldn't believe the unbelievable level of, you might say, of self-worth that these people had. And then a guy came from India who never took a course, and trying to think that guy's name. Does anybody know what I'm talking about? A very famous mathematician. Well, this guy comes there, and he's proving things that they have no clue on how he's doing, and he starts showing them. Remember, they look down at the Indians. This is back in the day when the British ran the world. The sun never set in the British Empire. And this guy's name is Ramanujan. Have everybody ever heard of him? Oh gosh, you gotta read this. This is another book. And Ramanuja comes there, and all these great masters are turning into fools. This little boy from India that never had any formal training, and he had the insight, he could see things. You know how I told you Gauss came up with that when he was in second grade? He had that kind of level of insight. So he was really good, Ramanujan, and then Paul Dardèche, the modern era, and those are the two great ones. If you like science, mathematics, engineering, you ought to read that stuff. And of course, about Richard Feynman. Now, I'm allowed to do that because this is a summer class, and I'm supposed to give you encouragement somewhat. That's an encouragement. It'll draw you, believe me. You'll love this stuff. So anyway, now getting back to this. All those books made an impact on me. Getting back to this right here, remember that is the electric field for an isotropic radiator, right? And here's the thing you circle. Right here, circle that. That's called the element pattern. The actual isotropic radiator had that element pattern. Do you all see that? That was, just one single isotropic radiator radiates as I e to the minus j beta r over r. Do you all agree with that? Right. At least in my world it is. This is a magnitude term that I'm going to talk about. Really, it does have a sign, and this is nothing but a phase term. So let's take a look at sine of n psi, just the function of psi, of sine of n psi over 2 divided by the sine of psi over 2. Does anybody know what that sort of looks like? What's sine of pi x, or sine of x over x?
It's like a sync.
Sync, right? Sine x over x, right? Isn't that simple? This is close, because if n is large, this is changing very rapidly versus the value of psi, where this is more or less slowly changing. And by the way, sine of a number, if that number is small, is about that number if you're in radians. Follow me on that? You remember sine x is about x for small values? Well, what this looks like when you're at psi equals 0 right here, it's going to have a value of n. Now the way you can find that out, the sine of 0 is by definition 0, right? So I have 0 over 0, and I have to use L'Hopital's rule to find out the value. Take the derivative of the top, derivative of the bottom. You see, when you take the derivative of the top with respect to psi, you're going to have an n over 2 pop out. Derivative of the bottom with respect to psi, you have really a 1/2 pop out. The 1/2s cancel, and you get n. So the magnitude here is n, and then it comes down, and it'll hit its first 0 when this upper one is equal to 0. Does that make sense? Because this one's changing fast. If you have like sine of 100 psi over sine of psi versus psi, the 100 psi is changing very rapidly compared to the bottom one. Do you agree with me, everyone? Now where's this first 0 right here? This is important. If you've had me for signals and systems, you probably know how to get it. Well, we don't worry about where this goes to 0, we worry about where that goes to 0. Now where does it go to 0? At 0, right? At psi equals 0. And at sine of, what's next? Sine of 0 is 0, sine of pi is 0, isn't it, right? So now we can set n psi over 2 equal to pi, or we can say psi equal to 2 pi over n. So this first 0 is a 2 pi over n, and this first 0 is a 2 pi, minus 2 pi over n. Suppose n's 100. It's 2 pi over 100. Okay. The next 0 would be at 2 pi, or 4 pi over n. But here's what happens to this. This is going to do one of these jobbers. Oops, that's too big. It's going to start getting smaller, like this, rapidly. The spacing on these zeros will be the same, but the amplitude goes down. And I think this is about minus 13.2 dB below. It's about the same as that for a sync function. The first side lobe is about that far below in terms of magnitude. Understand, class? Do you remember the 13.2 dB below for the first lobe of the sync waveform, the second lobe? Remember that side lobe business at all? No. If you don't worry about it. Just thought you might. So that's what this function looks like. Also, that first zero, and listen to me, that corresponds with psi, right? Psi is equal to beta d cosine of alpha, right? Plus beta d cosine of phi plus alpha. And that zero corresponds to 2 pi over n. Correct, class? That would be the first zero. Now, actually, that's a misnomer. The first zero is when it's zero, isn't it? That's when it's a maximum, right? And so what you do here, write this down, that when this equation is zero, see, that's the first zero, that's how you get the actual beam width, but don't worry about that, that's later. But where you get the maximum value is setting it equal to zero. Now, there, what that tells me is the beam will have a maximum value when that psi equals zero, or when beta d cosine phi plus alpha is zero. Follow me? And here's how you beam steer. I want you to watch this. So if I take alpha to the other side, so it's minus alpha, and then I divide that by beta d, that's the cosine of phi, right? So if I want the maximum of the antenna to be, I mean, if I want it vertically upward, straight up, I just make alpha zero, right? I can make alpha zero, and then when I solve for phi, I can see it's 90 degrees. Try to get a picture in your head of what this looks like. If this is my array here, and alpha, or I'm saying it's alpha, I should call it phi, is measured from there. Well, assume I want the actual maximum value of the signal to be broadside, radiated directly perpendicular to the beam, okay? Then if you take a look at that, well, then you would want what? This angle is what, class? 90 degrees, right? So we would want alpha to be zero in this case, because, alpha would be zero, but here's the reason for it, that if alpha was zero over beta d, that's zero, and that would be the cosine of 90 degrees is also zero. Now, actually what you normally do is take this and take inverse cosine of that equals alpha. Calling it alpha, equals phi. Y'all follow me in this class? But this is basically the equation that gives you the max direction. Maximum radiation in phi. Now, if you want the maximum radiation in some other direction, not broadside, then you go ahead and you can calculate alpha then. Then you can calculate what phase shift you would need, progressive phase shift, to steer the beam. Does this make sense? Think about this. If this is the equation for where the maximum of the beam is, the greatest, the electric field is the largest, then if we wanted it to be at any angle at all, suppose you put whatever you want there, then I can say that alpha would be equal to minus beta d cosine of the angle that's measured with respect to the axis of the ray, and it would allow me to beam steer it to this angle. Do you follow me? That's called beam steering, and we'll talk about that a little more later, but for now, just get an appreciation of it. Now, what I've showed you so far is something where this is the electric field element pattern, this is a phase, and this is a well, it's not magnitude. Yeah, it is magnitude, sort of, but now I'm going to say something more that's a little more useful. In general, the electric field from an array, the total electric field, please write this down, is going to be the electric field of the element. Whatever element you have, and that'll be a function of theta and phi and r, but theta and phi for sure, all right? So it's the electric field of the element, and it is a function of r. I don't like putting that in there, but it's also times the array, so that would be the array factor, and I call it E array. And that's a function of only theta and phi. So in general, E total will be equal to the element pattern. I'm just gonna leave it as E element, and we'll talk about a couple of elements. It's a function of, I'll put it the right way, R, theta, and phi, times the array, which is going to be E to the J, n minus one, and then it's going to be alpha, or I'm sorry, n minus one psi over two, times the sine of n psi over 2 over the sine of psi over 2. And here again, psi is equal to beta d cosine of the angle phi that's measured with respect to the array plus the phase shift. Now, this is true for, what I've done here is I've gone and shown you how an array function for the simplest possible type of beam steering, but it's commonly used. I have the same current, therefore the same power in each element. And I progressively change the phase of that in a way that will allow me to steer the beam. So if it's 0 degrees, 20, 40, 60, and so forth, but when I wobble that phase angle, all of them wobble the same way, percentage-wise change. And I can steer the beam anywhere I want. Here, that element has a definite pattern, all right, that's given to it. Half-wave dipole, short dipole, and so forth. Are you with me? So now we're gonna take a look, by the way, if that's the electric field, then what would the power be? The actual radiated power. That's what Dr. Wentworth's book has. What's the relationship between electric field and power density? PAV, or he calls it PAV, it's power density, is really what? 1/2 magnitude of E field squared over eta. You agree with that? Now, here's what happens. When you do this, you get rid of this term. That goes away because the magnitude of that's 1. So for this one, you're going to get, when you do this, you're going to get the power of the element in the elements pattern. So really, I'll just call it PAV of the element as a function of R, theta, and phi. Then it's multiplied by this squared. So he'll have in his book the sine of n psi over 2 over the sine of psi over 2 entire quantity squared. And that's the way he'll have it. But this is going to be the power pattern of the element, and this is going to be times sine squared of n psi over 2 divided by n psi. And I want you to take note of one thing. Remember I told you that the electric field would have, the array's effect on the maximum value of the electric field brings it up by n, right? Right here? Y'all see this one? The maximum, instead of being an E field of just 1, right? 1 times the E field of your isotropic radiator, now it's n. Well, in power, you square E field, so it's n squared, which means that this function right here, the sine squared, the squaring of the sine of n psi over 2 over sine of n psi over 2 has a maximum value of n squared. Okay? It's real important you notice that. So now let's talk about power pattern. You actually encounter something that would make sense talking about this. Let me show you this one. Wentworth's book has a lot, but I want to do this in a way hopefully you can all follow me. What I'm going to do is do simply 3 elements that are short dipoles, and we're going to talk about the effect of the array and each pattern and the antennas themselves. So here's what it looks like. I'm going to take 3 dipoles, short dipoles, and I'm going to align them like this. Okay, 3 dipoles. I'm going to have this one have a current I naught. This one have a current I naught e to the j alpha, and this one have a current I naught e to the j2 alpha. Okay. Now, I'm going to get the electric field at a distance r, and let me do something for you. Let me say the distance between here and here. Actually, let me do this. The distance between centers of the antenna, between here and here, call that D, and between here and here, D. And we're gonna let D be equal to lambda over 4 in time, but for now, just leave it as D. Are you with me? All right, now, remember that the angle I used, it was phi that measured the distance or the angular spread between the actual axis of the array and the vector R? That's this vector here. All right? That was what I called phi, didn't I? We can also say that Z in this case, if we assume this is the Z axis, can't we assume this is just theta as well? In other words, the angle is interchangeable. Do y'all see this? Remember that angle that he's using, the symbol phi, it is not the phi that is measured from the x-axis. Phi is an arbitrary angle that's always has to do with the measurement from the array's axis to the vector R, that angle. It's always a small angle too, the minimal distance. So this is that, and then the E field here, now these are all short dipoles, so I'm gonna stipulate this is a short dipole. And furthermore, let me say that the length of these dipoles, this length, L is equal to lambda over 10, all right? So that's how long they are. With me? Now watch how this goes. When I say the E, first I said to get, in general, E would be equal to the element pattern, right? I take the element pattern. Well, for a short dipole, the way they're arranged, the E field from just one of these would be equal to J eta beta, right, times I, right, it's I naught in this case. Then it's divided by 4 pi R. It's times the length L, the length in lambda, correct? And then there's going to be the E to the minus J beta R. R in this case will be measured from here, the center of that. And then it's times the sine of theta. Now that's the element pattern in the A theta direction. Do you all agree with that? Okay. Now I take this and I multiply it by the array pattern. I call this the array pattern. Wentworth's book will have F. His F is squaring this array pattern. He uses it for power. Now I take this and I multiply it by E to the J n minus 1. Well, n minus 1 is really 2. N is 3. It's going to be E to the J 3/2 of really psi. And then I multiply this by the sine, right? The sine of n, which is 3, right? Of 3/2 psi over the sine of psi over 2 in the A theta direction. Here again, psi in this case would be beta d cosine of the angle, which is theta in this case, theta, plus the phase change. Well, beta d, beta is 2 pi over lambda. Once I have beta d cosine of that angle, plus alpha, remember, beta is 2 pi over lambda, right? And what was the length of those antennas?
5.
Lambda over, can you see? Lambda over 10, right? So it's times lambda over 10 cosine of theta plus alpha, or it's pi over 5, right? Pi over 5 times cosine of theta plus alpha, and that's psi. And then, I'm just going to tell you this, you would go in and do the beta is 2 pi over lambda times lambda over 10 here, so you have pi over 5 in there. I didn't give you a value for I naught, but this is the equation that would give you the electric field's value at any point R and any point theta. Follow me, class? Yes, sir.
Wait, so for the sine, it says BD cosine theta, but the D is lambda over 4. You put the length.
That's the, No.
So it's-
Oh, wait a second. You are right. I am very sorry. You're absolutely right. Thank you so much. That's lambda over 4. I am so glad you said that. You're absolutely right. So that means this is pi over 2. Thank you. That's what I actually was going
Okay,
to
so I was confused.
That's my bad. I'm thinking, well, I was thinking wrong. That's absolutely right. I wanted to make the spacing be a quarter wavelength, but the length of the antennas be a tenth of a wavelength. Everybody with me on this? Thank you very much. So this would be, now this L right here would be the lambda over 10. Right? So this beta lambda would be pi over 5. This will give you the value of the electric field. Then to get the value of the power, you would take that square, divide it by 2/8, and that would be the power density, right? Now usually what they do is when they plot these power patterns, they get rid of everything but the angular variation. They only look at how a pattern varies versus angle. So they'll delete out, or they really normalize is what a lot of people say. But you will not see an all or anything like that. They just show what's called the power pattern of an antenna. What I did there is put it up, and this is the thing where you would plot that with MATLAB. You wouldn't sketch it by hand. You could if you wanted to, but the thing about these things is, I mean, there's tricks to do this. Nowadays, with the advent of computers, you're not going to spend the time sketching this thing with your hand when you can just plug it into a computer and do a polar plot in a heartbeat. And you can adjust it. What I'm actually going to do is, and an assignment I'm going to give you, is ask you to take this basis equation similar to this, and then vary it versus phi, and watch how the actual pattern changes. And I'll give you a little more information about that, all right, in the MATLAB assignment. I might collect that one too for some extra credit. All right. So that's basically how an array works. And I'll say this too with arrays. It doesn't happen, I mean, if you take Dr. Riggs' course on antennas, you'll learn a lot more about this. You don't have to have a progressive phase shift that's the same. As a matter of fact, you don't have to have the same current on each antenna. This is a common thing because it's easy to do and allows the mathematics of beam steering to be clearly understood. But what sometimes they do is they have something with the actual antennas that start and finish the actual array have a smaller magnitude of current than the ones in the center. There's a reason for this. They minimize the side lobe values. And they get a more progressive phase shift on the outer one, less shift on the inner one. And they start the phase shifting at the center lead, or the center antenna, not at the very end. And there's a lot of different variable things you can do to get what you want, more or less. If they want minimal side lobes, they do it one way. If they want the minimal beam width, they'll do it another way. There's all these other things. The one I've showed you is the most common, it's the simplest, and generally that solves most problems for beam steering. All right, now, a couple things I gotta talk to you about. Next thing is polarization mismatch. Now let me explain this to you my way. If I have an antenna like this, oriented this way, another antenna oriented this way, you see the electric field that would be radiating to this one is vertically polarized. Do you all see that? Right? It means when it hits this antenna, the projection or its length is directly impacting this antenna, right? Now, if I do this, if I take this antenna that's transmitting and I turn it a little this way, well, then the actual component of this electric field that's projected onto this antenna is going to be reduced by the cosine of that angle. Do you all see this? And eventually, and it will be less power. When this happens, when the receiving antenna is 90 degrees to the transmitting antenna in terms of just looking down a bore sight, then no electric field from here is going to be absorbed there. That's called a polarization mismatch. Do y'all follow me? It's important that you understand this because when you get, I'm level with you. You have no idea how bad some technicians are. They're given specs and they say, put the antenna up. If it's a dipole antenna, almost inevitably, it's assumed they're going to vertically orient. But that ain't the case. Some techs will do this because it's easier to mount or something. And then you get a guy down here who's got a vertical one, and it's a polarization mismatch, and there's no signal communicating, and nobody knows why. So the guys in the booth, you might say, back at the station are talking. This happens in the Army a lot. Stuff like this happens all the time. And then when they finally take a picture of it, they realize it's mounted wrong. Now, I don't know if that's a common problem in the Army, but I know this kind of stuff happens if you don't understand polarization mismatch. So, here's what it amounts to. If you have an antenna here, and an antenna here, and this antenna, I'm trying to draw this. I'm not trying to draw this where it's bent in the plane of the board, but I'm trying to make it bend like out of the board, if you know what I mean. How about if we look down the broadside axis? Suppose this is antenna 1, and this is antenna 2, looking right down the axis. The angular tilt difference is this, and the polarization efficiency is given as E, I think it's EF in his book, and it's really just the cosine of the tilt angle squared. It's more or less the difference between the orientation of this one and the other one in terms of the angle, the cosine of the angle between them. Can you all understand what I'm saying here? You gotta look down the barrel of this thing kind of sort of to get an understanding. That's all polarization mismatch is. So if you have a polarization mismatch, and say I have two half-wave dipoles, and you want to calculate the power received, well, the power received would be just like before, gain of the first, gain of the second, power transmitted times the quantity, lambda over 4 pi r squared, right? Just as before, but then you would multiply by the efficiency. All right, and that has to do with antennas when they do this. Now, suppose you have an antenna like this and one like this, and this one's not broadside to this or this. Well, then there's what? There's the gain decrease from this antenna to this one, right? Remember, like the problem I gave you, there was a gain decrease. But then if you take this one and tilt it, say 45 degrees, then there's the polarization mismatch as well that you'd have to multiply it by. Follow me? Can you all get a handle on what I'm saying there? All right, next, and the last thing I have to talk about today, and then we're basically done with this chapter, and that is the receive power. You know how you calculate receive power from the Friese equation? That's not how much power you can get to a load. That's how much power the antenna accepts. Now the fact is this, only half of that power can ever be taken out from the antenna. The other half creates currents in the antenna and re-radiates electric field, another electric field. All right, so only 1/2 of the power can ever be got. So if you think about an antenna, write this down. Here's an antenna as such. Comes in, we've got some incident power density, call it P av incident, right? I get my P received. This is the calculation. P received would be the aperture of the antenna times average power, right? So this is P received. It's the aperture, or you could say it's equal to lambda squared over 4 pi times the gain of the antenna times the average power density incident on the antenna would be P received. Are you all with me on this one? Just hang in. Now that power received comes in here, and we're going to attach a load to it. In this case, the load is going to have a value of the radiation resistance. The reason is I know an antenna, when it's transmitting, has a radiation resistance associated with it that deals with how much power, it has to do with how much power is radiated by the antenna. Do you all remember that? Yes. So please watch me. So one thing I can do, I can say that this little thing where I have an incident power received, P received here, and I've got a radiation resistance here. What I can do is say that I can model this as an open circuit source, V open circuit, that I'll calculate in a second. Then I'm going to have an internal to the antenna, a radiation resistance. Now this part right here is all internal to the antenna. And then, if I want to get the maximum power out of any system, what do you always make the load equal to if you have an internal source resistance? Maximum power out. Yeah, the two resistances will be equal, right? That's called impedance matching. well, it's not exactly impedance matching, but that's something you look from, learn from Dr. Irwin. You would make the load R rad, right? Now, let's see how much total amount of power these two resistors get. And I want you to think about that. Well, power received, if it's a sinusoidal wave, P received would be equal to 1/2 times the open circuit voltage squared divided by R rad. Isn't that right? You take the open circuit voltage and divide it by 2, not R rad. It would be 2 R rad. It would be the series. It would be the total of the resistances. It would be 2 times R rad. Or it's 1/4 R rad times VOC squared. Y'all agree with me there? Now please watch this. This is a very subtle thing. That's the total amount of power that you can receive. So the open circuit voltage associated with this, VOC, would actually be equal to 4 times R rad, right, times P received square root. This is the one you get down. The open circuit voltage is 4 R rad P received, or it's equal to this. Now, let's suppose I don't have a load that's equal to the actual R rad, and that's the case a lot of times. Then I can say that how I'd figure out the amount of power I'd actually get out of the antenna. I would put the open circuit voltage there, and I would put the radiation resistance here. And in truth, the fact is, there could be also an impedance, there could be a reactance there. Like if it was a dipole, an actually exact half-wave dipole, it would be 73.2 plus J 43.5. Are you with me? And then to get the most power out, you would put 73.2 minus J 42.5, so the J's cancel, the reactive component will cancel. So only the radiation resistance matters with calculating VOC. That's what I wanted to get at. But anyway, I'm going to put radiation resistance there. Then you would put any reactive antenna, JX antenna, whatever the internal reactive value would be. And then you would connect your load. Then Z load would go here. And then you could find out both the voltage, V load, and you could calculate power load. V load would be easy, right? It would just be VOC times Z load over Z load plus R rad plus JX of the antenna, right? And then the power would be what? It would be simply, if I wanted the power there, it would be 1/2 VL times IL, or times IL conjugate, and the real part of that. Or I could do it several other ways, but I'm just going to leave it like that for now. I know I've kept you. And let's see, we come back on Monday, right? Some of you have tests Friday, good luck. I don't know. How many do? 1, 2, just one? Anybody else? Okay, well, good luck. I'm going to give you an assignment with MATLAB for plotting some antenna, 1 and 2 antenna patterns. And we're done with this chapter. So I gave you a whole, no, I didn't give you this. I'm going to give you several more problems to do with solutions, but I am going to probably collect another one. Okay?
On Monday?
Unless there's an overwhelming reason not to. And you're going to be gone Friday's our test, right? You're going to be gone on Friday. All right.
So like you're gonna go to one that's not in the book?
Yeah.
Okay.
It's a couple
Make sure it'd be
habits.
obvious which one we're supposed to turn in.
Well,
Alright.
do them all anyway.
Yeah.
Are you guys understanding why I'm teaching this stuff? If you do the homework, you won't have any problems.
Yeah.
Because the homework just, it more or less illustrates all the stuff that I'm speaking about in class, or tries to at least.